Hello, everyone. Welcome to the third week of the course, An Introduction to Machine Intelligence for Architects and Other Non-Engineers. So before I start presenting today's topic, I will, as always, make a small review of what we did last time. It will be only 5 minutes, so that you can kind of come back to where we were. So this image, I hope you all know it by heart already. What does it show? How I introduce this is as a kind of different perspective to derivatives, which has to do with secant and tangent lines. What I did is I introduced the secant line as a line which touches the curve at least 2 points. And this kind of secant line shows us that there is some kind of average interval happening, because we have 2 points and then we want to calculate what is the, for example, derivative of speed in terms of time. We have 2 points in time. This is how we introduced derivatives originally. And then the question was, what happens as dt is approaching 0? So then, as dt is approaching 0, this ratio of ds to dt is approaching the derivative. And what happens at the same time in terms of this secant line? So at the same time as dt is shrinking and approaching 0, the secant line is approaching a tangent line at the point t. So from 2 points, we now went to a tangent at a single point in time. And now we have here a function sine of x squared, and we have its derivative. And you remember that I showed both functions graphed on top of each other and what are their relation. But now let's describe the red line, the derivative, as kind of not as a function, but as a tangent to the green line. So for every point of x, we take the output and then we create a line on top whose slope is equal to the derivative at that point. Then we can visualize the derivative as the slope, yeah? So the red line indicates the slope, and how this slope stands in the relation to the original function. Since we know that this slope kind of corresponds to the value of derivative, we can ask, okay, what kind of derivative values can there be for at a certain point, yeah, when we evaluate them? So a derivative value can be a negative value, it can be a positive value, or it can be 0. So then we can look at what kind of line slopes correspond to them. So for a positive derivative value, we have a positive slope which takes this range. And for the derivative value, we have 0 slope. And for the negative derivative value, we have negative slope. Yeah? And we used this last time to maximize or minimize functions output. So to maximize the function's output, you all know the steps. The formula is x new is equal to the x old plus the derivative times some kind of small number c. We'll see today that this number c is called a learning rate in machine learning. But yeah, let's not get ahead of ourselves. In the same way, if we want to gradually minimize functions output, the formula is very similar, except we have a different sign in front of the derivative. So we are now subtracting the value of derivative multiplied by a small number from the x old, and we get x new, which will minimize the output of this function. And then we also introduce the sigmoid function, and we will see today why is this function actually useful. We will actually use it. But as you can see here, what it does, it squishes its input to a narrow range between 0 and 1. So if you have a very low value, negative 1 million, the output of this function will be very close to 0, very, very, very close to 0. And if you have a large output, we have this output mapping to a value which is probably very close to 1. And then in between, you see this input range from -2 to 2, then you can see that this function kind of smoothly morphs between large values and small values on this very short input range between -2 and 2. Of course, if you evaluate it at 0, it's equal to 0.5. And then we also introduce multivariable functions. On the example of multiplication of two variables, we introduced the concept of derivatives. So what we have learned is that instead of computing one derivative, if you have multiple inputs, in this case 2 inputs, we need to compute 2 partial derivatives, yeah? And one is derivative of the output in terms of x, which is this delta f of x comma y in relation to delta x, and another is the derivative of the output in terms of y, yeah? And the first one asks how changing x influences the output to input ratio, and the second one asks how changing y influences the output to input ratio. By defining partial derivatives, this made it possible for us to understand and introduce the concept of a gradient. So gradient is really nothing special. It is just a list or a vector of functions' partial derivatives. So if a function has two inputs, you have two partial derivatives, so this vector will be of length 2. So it will have two numbers or two dimensions. I told you that if we know these three functions and their partial derivatives or normal derivatives, then we can compute the gradient of any neural network. So we can kind of construct machine learning models. And this is what we are going to talk about today, finally, for some of you probably. I will start by introducing one very old model. It was invented in 1958 by Frank Rosenblatt in the USA. It's the Perceptron model. And this model was actually originally devised to be implemented in a physical machine, not as a computer program. But of course, we will implement it in computer code. So what is this thing about? Let's look at this sketch. This is some kind of device which has three inputs and a single output. It doesn't have to have three inputs, you can have as many as we want. For example, a decision that we would be interested to make could be, should I go to the movies tonight? There is some cool movie playing. Should I go and do it? And in principle, what I'm interested in with perceptrons is a yes or no. So it's a very strict decision. There's no, maybe involved there. It's a very strict decision. And then I can ask some kind of questions to help me decide. And one of the questions might be, is it raining outside? Again, it doesn't take maybe. The output will be either yes or no. Is it raining or it is not raining? The second question might be, do I like the director of the movie? Yes or no? And then I can also ask, did my friends like the movie? Let's say that these are kind of important questions for me to decide, should I go and see the movie? Yeah. And then imagine this does not need to be limited to a kind of single layer perceptron unit that we had here. It can be a network, yeah? So whether I will go to see the movies, this can be one of these nodes, and then this could inform the next node, and then according to the next node, I will decide something else, and then at the end, I will decide whether I will study architecture or not. But it kind of has a certain quirk, which is that is binary. It is a binary model. And remember this thing that we did last time? Yeah, we kind of calculated what are the partial derivatives of this kind of chain. Yeah, do you remember this? So I will show you a perceptron circuit diagram. So this is all the mathematics that goes inside two-input perceptron. Yeah? As you can see, this is kind of something very similar. Yeah? When you see the perceptron circuit diagram, that you're not kind of overwhelmed, like what is this complexity here? It's kind of, there are many things that we already know. There is this multiplication, there is this addition, and then there is one more unit there, which I'm not sure what it is, yeah? But yeah, we will figure it out. What elements are there to a perceptron network? So, as you can imagine, certain aspects of our decision making can be more important than the others. For example, is it raining outside? Yes or no? But then I can ask how important it is if it is raining. Yeah? Is this some major criteria, or this is something not so important? So you can kind of weigh certain decisions. So how do you do it? If a decision is not important, you can pick a small weight. If it's a very important decision, you pick a large weight. Yeah? So then, do I like the director will be weighted with a weight which will determine how important is that I like the director. Yeah? And then there is another value, which is called a threshold value. This is the value which will yield the positive decision. So how does this thing work? You multiply the weight with, is it raining outside, yes or no? So if it's raining, it could be 1 or 0. Do I like the director is 1 or 0? But the weight, this can be any kind of number. It doesn't need to be 0 or 1. It can be 5, it can be 3, it can be whatever, 0.5, yeah? Then you multiply them. You add these weighted sums of weights and questions. You make a sum of them, and then you ask, is this sum that I just made, is it smaller than the threshold, or is it larger than the threshold? If it's larger than the threshold, then output 1, or yes. If it is smaller than this threshold, I will output 0. And this is how we can define a decision-making process by using a perceptron network. Okay, so if you want to write this mathematically, this is a piecewise function, so it might be like, looks complicated for you, but it's actually very simple. It's a function of two inputs, and the inputs are actually my yeses or nos. So yes to if it's raining, or no if it's raining, and yes, do I like the director or no, do I like the director? These are A1 and A2. And the function says it will output 1 if this weighted sum W1 times A1 plus W2 times A2 is larger than this threshold, which I need to choose. Otherwise, I will not go. So otherwise, the decision will be negative. It will output 0. But in principle, we do not have to look at this whole piecewise function. We can just concentrate on this part. Yeah, this is the important part that you should take into consideration. So let's make an example of this. Should I go to the movies? It's the same thing. It's the same question. And how important is it that it is raining? So this is, for example, I put the weight 2. Yeah. And then how important is that I like the director? I say, okay, this is a little bit more important to me than if it's raining. So this is I'm going to weight this with 3. And then what threshold value will yield the positive decision? I will say 4. Yeah. Let's now rearrange this thing just a tiny bit to change the meaning of this expression. Yeah. So what will I do first? I will look at this t on the right side, and I want to put t to the left side of the inequality. Yeah. When I do it, it becomes negative t, and on the right we have, is it larger than 0? Yeah. This is a simple algebraic operation that I just did. Then I can say, how does this change the diagram itself? Well, it changes in this way. Now we have another input, which is negative t, which is added to this weighted sum. If the sum is less or equal than 0, output 0, and if the sum is bigger than 0, output 1. So this is how we change it. Now, this negative threshold, let's call it b. And this b means bias. So let's replace negative t with b. When we do that, we have this expression W1A1 plus W2A2 plus some kind of bias is greater than 0. And this is now a fully working perceptron circuit diagram. And you can think of this bias as a measure of how easy it is for this perceptron to output 1. Yeah? So for a perceptron that has a very big positive bias, then it will be very easy for the decision to be yes or 1. Yeah? Because any weighted sum plus a large positive value will easily be greater than 1. Yeah? If you add to any kind of multiplication, add a very big number and ask, is this bigger than 0? Probably it is, because this big number is going to weight it towards the positive decision. Yeah? And then if this bias is very negative, then it's very difficult for us to make a positive decision because it will pull it towards the negative. Yeah? So this is the meaning of bias. Okay. In our example, we had this on the left, and now we rearranged 4. We put it on the left side. This is how it looks now. So 2a1 plus 3a2 plus the negative 4 is larger than 0. So we get this inequality. Let's evaluate all the possible decisions in our decision-making process. So we have the diagram on the left, where we need to multiply 2 with the first answer, 3 with the second answer, and add the negative 4. So our possible answers are 0, so negative for the a1, and positive for the a1, negative for the a2, and positive for the a2. And we can make this table on the right with all the possible choices that we can make. So we can make 4 choices in total. Yeah. It's not raining and I do not like the director. It's not raining but I like the director. It is raining but I don't like the director. And it is raining and, or which one is left?
And I like the director.
And I like the director. Yeah. So all possible choices are there. And then when we multiply with this 2 and 3 and add the negative 4, we get some kind of outputs that I will go to see the movie if it is raining and if I like the director. And now, I don't know if I should talk about this, but I don't know how comfortable you are with logic. I now want to make a kind of intellectual exercise to see how does this relate to logic in general. Do you know what logic is about? Should I remind you? It will not last long. So what is logic about? Yeah. So in propositional logic, you have some kind of symbols that we work with, for example, P and Q. And these symbols stand for statements. So one symbol, P, means, it doesn't mean, it says it is raining. Yeah. It has subject and predicate within this statement. Q might be, I have an umbrella. Yeah. And then this is a linguistic form which expresses something about the world. So it doesn't have truth within itself. So this statement, it is raining and I have an umbrella, it doesn't have any truth to it. Yeah. It's completely truthless. Yeah? It just asserts a possibility that some state might exist in the world. Yeah? And what logic does, it offers a mechanism or a model that can evaluate these statements according to what is called a logical reality. So it's a reality that logic gives you. And then statements can respond in two ways to this logical reality. So if they match the logical reality, they are true statements, and if they don't match them, they are false statements. Yeah. So logic creates kind of all the possible logical outcomes or possible realities for a single statement or a group of statements, and all statements are evaluated by answering whether they match this reality or do not match this reality. Yeah. In this respect, the statements can be seen as true and false. Okay, now I will go to an example. Okay, we have the statement, it is raining. This statement does not have any truth to it yet. Yeah, it is just a statement. You need to compare it to something to know if it's true or not. Yeah. Okay, what does logic does? Logic takes this statement and creates two realities. I will call it two logical realities. One reality is a reality where it is raining, and another reality is a reality where it is not raining. And then it asks this statement, first statement. This statement, is it raining? Compares it with a reality where it is raining. Yeah? So in reality where it is raining is a true statement. And in reality where it is not raining, the P statement, it is raining, is a false statement. You see what is going on. So when you look at truth tables, never forget what they are. Some people tell you, oh, it can be true or false. But no, it is true and false only according to the logical reality, not to a reality around us. So logic is very, very, how to say, it's a view on the world which is kind of very limited. It is either yes or no. Very much like perceptrons, yeah? So what we can do now, we can now make a table, truth table, of all the logical possibilities of this statement. So this statement has only two logical possibilities, yeah? Okay. Now this gets interesting. So what happens when you have two propositions? P says it is raining, Q says I have an umbrella. Yeah? And now logic, as I told you, constructs two realities for each of these statements. In one reality, it is raining. In one reality, it is not raining. In one reality, I have an umbrella. In one reality, I do not have an umbrella. Then you can ask, is it raining? And if in this reality it is raining, this will be a true proposition in this reality. In reality in which it is not raining, this will be a false statement. It is the same for an umbrella. But now what happens is that now we have four logical realities when we combine them. There is four logical, imagine like four worlds. In one it is raining and I have an umbrella. In another one it is raining and I don't have an umbrella. In one it is not raining and I have an umbrella. And in the last one it is not raining and I do not have an umbrella. This is how we can represent them, yeah? All the possible combinations, yeah? True and false for each one of them. So logic does not only provide these realities, but also kind of an instrument to compose additional logical realities by combining these propositions. So we can combine them, and then it proposes some kind of kit, like how can we join them together, yeah? And these operators are kind of inspired by language. So it is something that we often see it in language. Therefore, they appear very natural to us, yeah? But what is really going on is these compositions made by using logic only kind of provide rules how to proceed with this original statement, yeah? Okay, so what happens here? We have a statement, it is raining, and then we put a negative operator, yeah? So, not it is raining. Or, in language, we say, it is not raining, yeah? It is the same as saying not raining. And then, logic again constructs two logical possibilities. In one it is raining, in one it is not raining. And then asks, is it not raining? How does it relate to both of them? And then we say, in first, where it is raining, it is a false statement. In a second, is a true statement. So you see, if we have all the possible logical propositions for P, which is true and false, negative P will have the opposite ones, yeah? What used to be true now is going to be false. What used to be false now is going to be true. So it kind of switches the truth operator. And now, another piece of kit, it's called a disjunction. It's a logical operation, yeah? And disjunction only works if you have two statements, yeah? At least two statements. It doesn't work with one like negative, yeah? And this mimics OR within language, yeah? So if you imagine a situation in life, if someone has, I don't know, two pieces of fruit, a mango or a banana or whatever, and you can have only one of them, yeah? So imagine you do not have language. So how would you show to someone that you can only give him one of these objects? So either this one, but not this one, or this one, but not this one, yeah? So this is a very complicated game in life, and you can think of many ways how we should do it, and they are not very satisfactory. This simply is not something natural, yeah. But this whole complexity is removed if you just have the language, and if you can say or, you will have this one or this one, yeah. Just with this simple word or, huge complexity is removed from this situation, and this is in principle how logic operates within the language, yeah. So I do not want to say what comes first here, logic or language, because this is not a really important thing, but you can see them always kind of intertwined. And now let's see how this or works, how this junction works. So we have a statement which is combining two statements. One is it is raining, and the other one is someone is watering plants. So I'm asking, the combined statement is it is raining or someone is watering plants. And now we have these four logical realities. In one it is raining, someone is watering plants. In one it is raining, but no one is watering plants. And we are asking, it is raining or someone is watering plants. Is this a true statement if it is raining and someone is watering plants? Well, yes, because what I'm saying is that it is raining or someone is watering plants, yeah? So it must be true if it's actually raining and watering the plants. And it will also be true if it's raining but no one is watering plants, because it is raining or someone is watering plants. This is what I'm saying. So any of these will work. Finally, this statement is only wrong when it is actually not raining and no one is watering plants, because in this reality, if I say it's raining or someone is watering plants, this simply does not work, yeah? Because none of the options that are happening are offered in my sentence. So how can we describe this? So we can say we have two statements, P or Q, that the disjunction will be negative only when both statements entering into it are negative. So we can now symbolize this with symbols, with logic, yeah? Or we have the same with the word and. So this is a logical conjunction. It creates kind of complex propositions. So we have two statements, it is raining and someone is watering plants. And now we can also take that statement and compare it to these logical realities. And you will see if I say it's raining and someone is watering plants, this will only be true, this statement will only be true in a reality in which it is raining and someone is watering plants. In all other realities, if I say it's raining and someone is watering plants, but actually someone is not watering the plants, or it is not raining, then this is going to be false. And again, we can write this table like this. So conjunction will be true only when both propositions that enter it are true. In case you did not pick this distinction along the way, and you are maybe wondering, what do these logical operations such as conjunction, disjunction, negation, but also values such as true and false have to do with our perceptron decision-making machine? Well, there is a convention to represent logical true and false as numbers, as 1 and 0. So true is 1 and false is 0. And the convention is not really randomly based, because these respective elements do belong to isomorphic algebraic structures. So if we would like to translate the output of our decision process, which we now have written in zeros and ones, to the logical form, what we can do is we can just replace the elements like this, and we would get a truth table, yeah, like this one on the right. So we saw that conjunction, disjunction, and negation, they have their specific truth tables. So we might ask, is our truth table actually something that already exists in logic and computer science? I mean, our particular output of our network. Well, actually it is. So we had these weights 2 and 3 and the bias -4. And with this selection of weights and biases, we have this selection of outputs. And when you look at how they are distributed, the output is true only when A1 and A2 are true. In all other cases, the output is false. This is actually a conjunction, so it has the same truth table as conjunction. Now, what if we wanted, for example, to flip the values in this table? Yeah. So if the output was 1 in this table, now make it 0, and when it was 0, make it 1. So flip the values. So how can we do it? But we are restricted to only change the weights and biases of our perceptron. We cannot touch anything else. Well, the only thing we can change are these numbers, 2, 3, and -4. Well, the interesting thing here is that we can flip the sign of our weights and biases, and then this will actually result with flipping the sign of the output of the network, yeah? So if I change 2 to -2, 3 to -3, and -4 to 4, then we get the output which is the opposite of what it used to be. Yeah. And now with these inputted outputs, do you recognize this distribution of truth values? Do you know what this means in logic and computer science? Well, this truth table corresponds actually to a so-called NAND gate. And NAND gate is a universal gate, meaning that any other gate, we can represent it with a combination of NAND gates. So you add NAND gates together, put them together in a network, and you can create any kind of logical gate. Yeah? And this property of the NAND gate is called also a functional completeness. So now, just for fun, we can deduce a couple of kind of bold statements, but these will help us later to understand better what machine learning is about. So, number one, NAND gates are universal, so you can build all other logical gates with them. Then you can implement an NAND gate with a single perceptron. I just showed you how to do that. You just need to pick appropriate weights and biases. Then you can implement any logical computation by a perceptron network because they're universal. And finally, if this is possible, then you should be able to actually build a general purpose computer based on a perceptron architecture, because general purpose computer can be implemented by using logical operations. And these logical operations can be implemented by an NAND. Okay, so this is our algebraic expression, or so-called inequality, which represents when does our perceptron or our decision-making device yields a positive decision. When it's less than 0, in all other cases, it's a negative decision. Well, if you're not comfortable with inequalities, let's simplify this a little bit and just temporarily make this into an equality. Yeah? Now we can use algebra to rearrange this expression a little bit. Yeah? We can put 3a2 to the left side and all other elements on the right. Yeah? So we get 3a2 equals -2a1 plus 4. Now what we can do is we can divide each element by 3. Yeah? So if we do that, we get that a2 is equal to -2/3 times a1 plus 4/3. Yeah? Well, if this still doesn't ring a bell, let's then replace a2 with y and a1 with x. Yeah? So what does this remind you of? Well, this is actually a slope-intercept form of a linear equation. So this is an expression that is the same thing as the line in two-dimensional space. In our original expression was as well, but maybe you do not know this form, so I just transformed the form of this linear equation. Yeah, and what is the slope of this line? Well, it is -2/3, so it means it's a negative slope. Yeah. And what is the y-intercept? Well, it is 4/3 or 1.33333. Yeah. Well, this means that our decision process, implemented by a perceptron network or a single unit perceptron, seems to be representable by means of geometry. Yeah? So this is very interesting. And what else can we deduce? We can deduce that it's most likely a linear decision process. Yeah? So let's try to plot this line. When we plot this line, we see that the line actually splits the 2D space into two regions, one above the line and one under the line. What corresponds to these regions algebraically? Well, these regions actually can be represented by our inequalities. Yeah? So for each value of x, what is larger than y is what is above this line, and what is smaller than y is what is below the line. Yeah? So, but do not forget that our inequality was actually the representation of our perceptron. So we need to think about what is the meaning of this line in terms of our decision process. So the line actually is a decision boundary between the positive outcome, which should be above, and negative outcomes, which should be under the line. Yeah. Now, since we made our table of all possible decisions according to the inputs, we can plot all of these inputs and outputs in our space. So now we have these 4 points. So what you can see is there is only one positive outcome, which is where the point is in the blue area, and 3 negative outcomes, which are all points in the gray area, and there is the line separating them. Our decision-making process is actually very similar to a classification problem in machine learning. Yeah? So in classification, you have, for example, 2 classes of things, for example, dogs and cats, and they are represented by data, of course, and you want to be able to predict, if you get a new photo, you want the computer to predict whether this is a cat or a dog, according to the data. Yeah? So to be able to do that, there needs to be some kind of boundary between what is a dog and what is a cat. And this is exactly what the red line is doing in our example. So it separates positive from negative decisions in our case. Yeah. Our interest might be then, from the perspective of machine learning, to learn what kind of weights and biases do I need to choose to have a certain distribution of outcomes. So if I want 2 positive decisions for a certain inputs, then what weights and biases should I assign to my questions? But then also you might see another peculiarity here, yeah? There are only 4 possible outputs in this whole 2D space, and they are very kind of symmetrically, rigidly distributed. So you can kind of see that the space of logic is very restricted in comparison to what the 2D plane allows, yeah? Okay, but then you say, the reason for this is only because we have only 2 questions, and if we have more questions, then things will improve, yeah. So you just need to add more questions, and then you will have more weights, and it will improve. Well, let's investigate this. So this is our last case, yeah. So what we realized is that if we have 2 questions answered with A1 and A2, then the decision boundary will be a line in 2D space. And what happens when we add, for example, the 3rd question with the binary answer A3? Well, now we have more possible logical realities, as we have discussed. So we have 2 to the 3rd power of states, which is 8. Therefore, our table now has 8 rows. Yeah? And everything else is the same. So the structure of the perceptron hasn't really changed. We only added 2 new elements, which is A3 and W3, and then we multiplied and added them to the rest of our products. And let's now try to represent this geometrically. Okay, since we have 3 varying inputs, they can be shown as points in 3D space. And if that's the case, then the decision boundary in this case is a plane. Now, by changing the weights and biases, what we actually do is we rotate this plane, and on one side of this plane we will get positive decisions, and on the other side we will get negative decisions. Yeah. So what we can actually deduce is that when we add more dimensions to our binary decision process, the space in which the decisions are contained is still kind of too large for the decisions themselves. Yeah, and this really is an inherent limitation of logical thinking. Also, one more thing to notice is the boundary. The boundary is very regular in this case. Actually, in both cases, it used to be a straight line, and now it's a plane. And when we think about this from the perspective of machine learning that we know today, then obviously this is a limitation. We cannot really expect that the real world phenomena that we would like to work with will be separable by such a strict regular boundary. Yeah, it would be much better if this boundary was something which is more flexible, that was non-linear practically in its space. Yeah. So we can deduce that there are some shortcomings to this perceptron model by looking at it from these perspectives that I introduced. So first, the inputs are binary. Therefore, a very small part of the space is taken into consideration. This is what we saw. In 2D space we have only 4 points, and in 3D space we have 8 points. Then the decision boundary is linear. It would be better if it was something more flexible. And the third thing is something that I will show a little bit later. It is really difficult to steer this function towards any kind of result because this function is actually non-continuous. Yeah, you will see that this is a function that is not actually differentiable. This is not a smooth function. Okay. So how can we then overcome? How can we upgrade this perceptron model to alleviate some of these shortcomings? Now let's see what neural networks are allowing us to do. Let's expand this model naturally by just thinking what happens if we would leave the space of logic and its geometrical interpretation. If we would stop thinking logically about saying it's raining, it's not raining, I'm going to see the movie, I'm not going to see the movie. But what happens when we introduce this maybe? So if I say I'm kind of 80% certain that I like the director, or I'm 30% certain that it's gonna rain, yeah? So this kind of introduces uncertainty, and let's see what this uncertainty then brings to this picture that we drew. So this was the old decision space that we had, these 4 points. When we introduce probabilities, we are actually introducing new points in this space. As you can see, there are infinitely many values for the weights and biases that we can put in this space. How do we do this technically? Instead of saying that answer 1 and answer 2 can only be ones or zeros, we simply use real numbers to encode the probability. So if something has 100% probability, something is a yes, then this will be another 1.0. If something have 0% probability, it's 0.0. And something in between will have 0.34, for example. My answer has probability of 34% of being correct, for example. Okay, then there is another thing here. We already introduced this diagram, this kind of schema of the perceptron model. And the question is, which element here actually enforces us to have a linear separation between points? What element here is making everything linear? Why?
Because it's a binary yes or no.
Okay, good. So this enforces a linear separation between points. The question is, how can we make this into a curve? Yeah. The reason why there's a nonlinear separation between points and why we cannot actually learn with this model properly is that this model that we introduced, if sum is less or equal to 0, output 0, or if sum is greater than 0, output 1, this is actually called a step function. Yeah. So this function has only two values. If it's greater than 0, it's 1. If it's less than 0, it's 0. Can we differentiate this function?
No.
Why?
Differentiate the step function.
Yeah, what would be the derivative of this function at the point 2?
It's 0.
0, because it's horizontal line. And for mean negative 2?
It's still 0.
And what would be for input equals 0? Infinity. So it's not defined, yeah? So it's kind of not great function for doing derivatives, yeah? But what we can do is we can introduce the sigmoid, yeah? So it sigmoid squishes all of these outputs in a range between 0 and 1. And you can think of it, if it's 1, then it's 100% probability. If it's 0, it's a 0% probability. And there is also some values in between, yeah? So now because we have sigmoid function, if we pass the output of our decision-making process into a sigmoid, sigmoid will make sure that it's somewhere in between 0 and 1, and there is a smooth transition between 0 and 1. So it's a kind of neat trick which sigmoid introduced. And also, can we differentiate sigmoid? Can we find the derivative of it? We did it last time, yeah? What is the derivative of the sigmoid function? Exactly. So the derivative of the sigmoid is the output of the sigmoid times 1 minus the output of the sigmoid. So very easy derivative. So you see we are getting somewhere now. Now we can actually enforce some kind of different separation between points which is nonlinear. Yeah? So we are getting somewhere. And how is this unit called when we add the sigmoid after the sum? Do you know? We call it a neuron. You heard of neural networks? It's a network of these things. Yeah? This is a neuron. Exactly that. So we have weights, which are real numbers, our answers or activations, which are real numbers, bias, which is a real number. This all gets multiplied together and then summed together. And then this goes into an activation function, which is sigmoid, which makes sure it goes between 0 and 1, and it's differentiable. Yeah? So now we can steer the output of this function to go higher or to go lower. And how do we steer it? Okay, that's the next question. What is the formula? Yeah? Sigmoid of W1 times A1 plus W2, A2 plus B. Yeah? If we have two inputs, this is the formula. Very simple formula. Yeah? If we have n inputs, it's just a sigmoid of the sum of all weights and all activations plus the bias. So if you have 100 of them, then it's a sum of 100 weighted sums. So W1A1 up to W100A100. Yeah? That's it. Plus B at the end, and that's it. Yeah? And then an artificial neural network is just a network of these units. There is something added on the end that I still didn't explain what it is, but that's it. That's what a neural network is. Okay, how can we learn with an artificial neuron? I will show you that it's possible to learn even with a single neuron. We do not have a network. We can learn with a single one. Yeah? Let's see how we could do that. Let's say that we have, this is our data. Yeah, we have 6 data points. And there are points in a plane. Yeah, they have x coordinate and y coordinate. And each of them has associated with it a label. What is a label in data? Label can be you have a pictures, and then label could be horse, a cat, dog, mouse, yeah? So there is some data, some numbers, and then we associate a certain label. In this case, our labels will be, for example, we can say that label is red points and blue points, yeah? And let's say that blue points will be the label +1, and the red points will be -1, yeah? But it doesn't need to be a number, label can be a text, yeah? But let's now make it simple, and now we have two classes of points. Ones are blue points, ones are red points. Blue points have the label +1, red points have the label -1. What do we want to do here? We want to fit a line that will separate these 2 points, yeah? We want to put a line which separates blue ones for the red ones, yeah? This is our model. Why is this line useful? If we have a line, we have something which is above it, we have something which is below it, yeah? So then if we add to this model a new point that our model has not yet ever seen, because we have this line, this model will be able to predict, will this point, new point without a label, will it be red or blue, you know? So according to our data, according to what we said is blue and what is red, and according to the line which separates them, we can predict any other point that we put in. We will know when we put this new point whether it should be red or blue. So this is what machine learning basically is about. This is what classification basically is about, yeah? Yeah, this is how you implement machine learning with a single neuron, but I will show you that I can even make learning even simpler than this, yeah? There can be even a simpler example than this. I can even remove this sigmoid, and if I remove it, then I will be able to separate these two classes of points with a straight line, yeah? So even with this very simple unit, I can do machine learning. This might look like a magic, but it's true. So how would I feed this model? So now A1 would be, for example, data point. And which data point? We have two data points. We have X and Y. These are our data points. And we have a label. So A1 will be data point 1, or X. A2 will be data point 2, or Y. So, you know, if we have a data point here, 1, 2, and 0.7, then A1 will be 1.2, and A2 will be 0.7, yeah? We can only look at one data point at one moment in time, yeah? We cannot just plug them all in at the same time, yeah? We do one data point at a time. Then we have a label. This is something that we got, yeah? What is the class of this point? It's +1 if it's 1.2 and 0.7. And then we randomly initialize some real numbers for our weights, yeah? They should not be very huge numbers. Let's say that they are numbers between 0 and 1. We just randomly initialize some numbers which will multiply our data points. And the output will also be a real number. Some number, it has no meaning. It will be 3.575, yeah? An output of this multiplication. Question is, how do we instrumentalize this output? How do we make sense of this output, of these multiplications and additions, yeah? So what we need to do, we need to somehow correlate the label with this output to somehow make sense of the output. We need to correlate the label with it. I'm not telling you yet how we're doing it, but this is the only thing we can do, yeah? How can we instrumentalize this relation between data points label and the current output of our neural network in order to make our network actually classify points? How can we make this work? Well, one of the possible solutions is this. I took this example from Andrej Karpathy's blog, The Hacker's Guide from Neural Networks. I thought it was a very good example. We can define that in our model, the weights W1, W2, and the bias B, which are, by the way, just real numbers, must be tuned such that the neuron, or our function, outputs a number greater than 1 when it encounters a data point associated with the label +1. Similarly, the function, or our neural network, should output a number less or equal to -1 when it encounters a data point associated with the label -1. So how does this work? In words, it's maybe a little bit complicated. Let's try to visualize this. For example, we choose a data point. This data point has X and Y coordinates, and it has a label. Then we compute the neuron's output and plot it on this number line. So we have 4 cases that can happen. First one is the output of this neural network is positive, and the label is +1. This is a correct outcome, and we should not do anything in this case because the network is correctly classifying our data point. The second example, we have a data point for which the neural network outputs a value which is less than -1, and its label is -1. Again, the point is being correctly classified. But then there are two more cases where we need to do something. For example, this. This data point has the label -1, but the output of the neural network for this point is larger than -1. Yeah? So what we need to do for this data point, we need to make it less than -1. So we need to minimize it. And finally, in this case, our data point has the label +1, but the output of the neural network for this data point is less than +1. Yeah? So we need to make it more than +1. To do that, we need to maximize the function for this output. Okay, these are 4 possible cases. Let's put them in a table. So, when the output is greater than 1 and the label is +1, we don't have to do anything. Yeah? But when the label is -1 and the output is greater than -1, then we need to minimize the output of the function. If the label is +1, but the output of the function is less than +1, we need to maximize the function's output. And finally, if the label is -1 and the output of the function is less than -1, we do not have to do anything. Yeah? And how can we minimize or maximize neuron's output? Yes, so PS, a neuron is just a function, and we already minimize or maximize the function. So we just need to compute the partial derivatives. That's it. You see how derivatives are important in machine learning. By computing them, you will be able to guide it however you want it. Yeah? And why is it even possible to compute derivative of an artificial neuron? Well, I already kind of answered that. Because the sigmoid function that we used, it's a smooth function. It's continuous differentiable functions. It has a derivative at each point. Yeah? So this is why machine learning works. At least neural networks work. All right, now just to remind you, what is this? This is a composition of functions. Is it a single input function or multiple input function? Is it a single? Yeah, the input is x, the output is z. And here we have a multivariable function. Yeah? Artificial neuron is nothing more than a multivariable function, and I have the function described. Output is equal to sigmoid of this weighted sum plus the bias. Yeah? So this is the function. We need to maximize that function or minimize. What is the derivative here? Again, I want to guide you through all the things. Yeah? This is what we are going to compute. Right now, we are not going to use the sigmoid at the end, make it simpler. Yeah? So we have data point 1, data point 2, and we have weights and biases. Because data points is something that we want to learn from, yeah? We do not change the data. So this is the first rule of machine learning. You do not change the data. Data is something that you tune the other things to. So we tuned our weights and biases to give us results that we want, but we do not change the data. Yeah. So I do not need to compute partial derivatives in terms of our data points. I need to compute only 3 partial derivatives here. One is the derivative of output in terms of the weight 1, output in terms of the weight 2, and output in terms of the bias b. If we use chain rule, we can simplify this operation. So instead of writing delta output over delta w1, we can simplify it by computing delta output over delta p1 times delta p1 over delta w1. Yeah? The second one, delta output over delta w1, we can simplify into delta output over delta p2 times delta p2 over delta w2. Yeah? And for the bias, we don't have to do anything. Yeah, bias is just going to be equal to 1 because there's just addition. Yeah. So then to compute delta output over delta w, we have simply to compute 1, which is the derivative of this addition, times a1, which because we have multiplication, and derivative of multiplication is always the other element. So it's just going to be 1 times a1. The derivative of the output in terms of w2 is just going to be 1 times a2. And the derivative of the output in terms of b is just going to be 1. And here's the gradient. So the gradient of this function n, which has 2 inputs, 2 weights and 2 biases, is just a1, a2, and 1. So these are the values for the gradient. Yeah? These are the values that we need to update in our learning model. And now if we add the activation function, if we add the sigmoid at the end, you see that not much has changed. Yeah? the variables a1, a2, and 1 are the same, is just what is in front of them is the derivative of the sigmoid itself, which is the output of the derivative, which is O, the output of the whole thing, times 1 minus O. You see, there's a common term here everywhere. Yeah? So if we want to update, for example, first weight, we simply need to take the old weight, and we want to minimize it, for example. We need to subtract the derivative, which is now this O times 1 minus O times A1, so this is our value for our gradient, times some small number c. Yeah? To minimize W2, W2 new is equal W2 old, and again, we subtract the derivative times a small number c. And to minimize b, we simply take the b old and subtract from it the derivative times c. Yeah, super simple. Let's now look at an example where we will implement what we were talking about so far, an algorithm to classify points, red points from blue points, by using only a single neuron, and also this will be a neuron without the activation, so a very simplified neuron. Okay, this first line, you might recognize this part here, we are importing NumPy, but all the other elements are only cosmetic elements or have to do with plotting, so with visualization. So they are in no way essential for machine learning, so you don't have to care about them, just run this line of code. Okay, now we have our data set of 6 points. As you can see, each of them has their respective x and y coordinates and a respective label. For example, first data point has x of 1,2, y 0.7, and the label +1. And now these points are visualized. All of these points are just simple 2D points, but then some of them are marked in red and some of them are marked in blue. And this is exactly the meaning of the label. If the label is +1, the points are red, and if the label is -1, the points are blue. So we are interested to somehow differentiate between them. And in order to differentiate between them, we need to make a boundary between these 2 points. So now you can imagine that the boundary would be a line that would look something like this. But why would such a line be useful? Well, it would be useful for so-called prediction. What is prediction? Imagine that we now introduce a new point, for example, a point here. If we introduce this point, our algorithm should tell us if this point is blue or red. But in order for the algorithm to tell us that, we need to have a boundary. We need to know what actually distinguishes blue points from red points. Well, if we have that the boundary is aligned here, then we know that from one side of the line are the blue points and on the other side of the line are the red points. So if the point is here, the algorithm should say, well, this is a blue point. And if the point is here, the algorithm should tell us, okay, this is above the line, this should be a red point. Okay, how to implement this in Python? We will use a simple linear function, which is this one. We already computed the partial derivatives and all of it. And this is how it looks like. So f of 2 inputs, x and y, and then what happens is these inputs are multiplied by 2 weights and by a single bias. So let's see what we are asked to do. It says if our data point is x, y is 1.2, 0.7, and if the chosen parameters are 1, -2, and -3, initialize the variables. Okay, we can do that. So we can write x is equal to 1.2, and then in the next line we can say y is equal to 0.7, but if we want to put it on the single line, we can just say x, y equals 1.2, 0.7. Okay, then on the next line we can do the same with a, b, and c. So a, b, c equals 1, -2, -3. Okay, that works. Now it says for the corresponding data points label, initialize the variable label. So let's see. The data point is 1, 2, and 0.7. Therefore, the labels should be +1. All right. Let's write it down. Label equals +1 or 1. It's the same. It's just a number. It's encoded as an integer. Now it says compute the output of the function f and assign it to the variable output. So how to compute it? Well, we multiply this one with this one, this one with this one, and then add -3 to it. Practically this means a times x plus b times y plus c. Yeah? So a times x plus b times y plus c. And the output is -3.2. All right. So for this data point and this label, this is the output of the function. Now it says assign it to the variable output. Okay, and I will say output equals this. And if I type output here, then it will print it again. Yeah. Okay, now how do we predict? It says we defined it in our algorithm. A, B, and C must be tuned in such a way, so we have it in the table how they should be tuned. So if the output is greater than 1 and the label is +1, do nothing. If the output is greater than -1, but the label is -1, then we should minimize it, yeah? If the output is less than +1 and the label is +1, maximize it. And if the label is less than -1, but the label is -1, then do nothing. So it says, decide whether we should minimize or maximize the output of our function for the current data point. Well, we already know what we should do. So the label of the function for this data point, 1, 2, and 0.7 is 1, yeah? But the output is -3.2. So label is 1, yeah? But the output is actually less than 1, yeah? So it's -3.2. So this is the case. We need to maximize this function. We need to make its output be greater than +1. And now it's -3.2. So we should maximize the output for the first data point. Okay, so now we are asked to create a Python function which is called decide and has two inputs. First one is the output of the neural network for the current data point, and one is the current point's label. And this function prints whether we should minimize or maximize our function f. Okay, let's do that. So def, decide, output and label are the inputs, colon, and then we say. Practically we need to implement what says here. And we have 4 cases, and in 2 cases it says the action is do nothing. So for these cases we simply do not need to implement anything because we do not want to do anything, yeah? So we have these 2 cases where we need to minimize output and then maximize the output, and this is what we should implement. So if output is greater than -1 and the label is -1, so I put 2 equality signs because I'm asking, is the label equal to -1? Yeah, so it's true or false answer. If I wanted to assign -1 to label, then it would have only 1 equality sign. But since I'm asking the question, it has 2. So if that's true, then we should minimize the function. Minimize output. And the second case is if the output is less than 1 and the label is equal to 1 or +1, it's the same, 1 and +1 is the same, then we should maximize the output. All right, now it says test the function decide for the current output and the current label and try some other values. Okay, let's try the current values. So decide for our output, which is -3.2, and our label, which is currently +1, it should tell us to maximize output. As we already said, we should maximize the output. Okay, now it says try for some other values. Okay, let's see what these are. Actually, let's make the third case here. So if this, all of this is not true, then else print do nothing. So this now covers these 2 cases here. If none of this is true, then simply do not do anything. Again, if I run it, it still says maximize output. But let's try some other data point. So let's try the second one, which is -0.3, -0.5, and -1. Yeah, -0.3, -0.5, and the label is -1. Okay, now the output is -2.3 and the label is -1. So in principle it should do anything. It shouldn't do anything. And now we ask decide output label, and it says do nothing. Okay, fine. Let's put back the original value. So it's 1,2 and 0.7, and 1,2 and 0.7, and the label is +1. So let's run this. Make sure that the output is the same as it was before, like this. Okay. And again, this side should say us to maximize the output. Now it says if the formulas for maximizing and minimizing functions are respectively these 2, we already know these formulas. So x new is x old plus or minus the derivative times some small number. It says how can we use a number holding variable, for example sign, to modify this function so that it can maximize and minimize according to its value. Okay, so what does it mean? We have these 2 formulas which differ only by this sign, plus or minus. So it says The idea is that we can have only one formula for both maximizing and minimizing if we replace this plus and minus by some variable sign. And this is exactly what we can do. We can make sign equal to either 1 or -1, and then depending on the value of this sign, we will either minimize or maximize. So what we can do is, I will write it as a comment, so x new is equal to x old plus sign times derivative of y over derivative of x times this c, this small number, yeah? So now if the sign is +1, we will actually run this thing and maximize the function. If the sign is -1, we will run this one and it will minimize the function. Okay, now it says initialize the variable sign to 0 and write code that will set its value to -1 or +1 according to the current values of the variables output and label. Well, this is practically the same as what we did here. So instead of now printing whether to maximize or minimize or do nothing, we can now initialize the value sign, and according to the same criteria, we can either say that sign is equal to -1 here, because it's minimized, sign is equal to +1 where we need to maximize, or sign is equal to 0 when we do not do anything. So how can we do that? We can say that sign equals to 0, and then we can copy this, or we can just type it. If output is greater than -1 and the label is -1, instead of minimizing, we will say that sign equals to -1. And if the output is smaller than 1 and the label is 1, then the sign should be equal to +1. And now we do not need this third statement else, because we already set the sign is equal to 0. If none of these is true, sign will simply remain being 0. Yeah? But if this first is true, sign will become -1, and if the second one is true, sign will become the +1. Okay, let's run this. And now it asks us what is the value of sign for the output of our current data points and their label. So we can simply type sign, and it will tell us +1. And +1, as we know, means this one, which means maximize, which is the same as this one, maximize output. Okay, so far so good. Now is the part where we compute the gradient, and we already did that, yeah. So for this function, we already computed the gradient. So the partial derivative in terms of the a is x, in terms of b is y, and in terms of c is 1. Now it says initialize the partial derivatives using the variables dA, dB, and dC and prints their values. Because I cannot make a variable delta a, yeah, because it's very difficult to type it, I will simply use dA, and I will mean the partial derivative, although d would mean a single variable function, but here I can make that exception, as long as I know what I'm doing. So I will just say dA, dB, dC equals, first one is x, second one is y, and the third one is 1. And now we assign these values. Now it says introduce the variable step size to hold a very small number and maximize the value of dA, dB, and dC. Yeah? Well, this step size, what is that? This is simply this c here. This is the small number that we multiply the derivative with. So instead of making it 0.01, yeah, we can simply call it c, or if we want to know what it is about, we can call it step size. So let's define the variable step size and set it to 0.01, for example. So now we do not have to type 0.01 anymore. Yeah? And what else it says? It says minimize or maximize the value of dA, dB, and dC. So it doesn't tell us whether to minimize or maximize, because this should be known according to the relationship between the output and the label. And this is what we defined with this, computing this sign. Okay. So how do we do that? So we can say that, for example, a new is equal to a old, which is just a, yeah? This is the three parameters which we introduced in the beginning, a, b, and c, yeah? So we can say that a new equals a old plus sign, which will be either -1 or +1, in our case +1 at the moment, times the derivative in terms of a, which is dA, times some very small number, which is step size. Yeah, we can do the same for b new equals b plus sign times dB times step size, and we can do the same for C. So C new equals C old, which is C times plus sign times dc times step size. Yeah. So if I run this, then we will create three new variables, A new, B new, and C new, which will take the updated value of the old values A, B, and C. But there is another way how I can do it. I can simply say, I do not wish to create new variables A, B, and C. I can just overwrite the A. So I will compute the updated A and just overwrite the old value. So just replace it. I will compute the new B and just put it in the place of the old B. And do the same with C. So now I update A, B, and C. A, B, and C used to be some numbers. When I run this, there's now some other numbers. Yeah. So for example, A, B, C is now, you see, these are some numbers which are not the same as our original A, B, and C. Yeah. They're now updated. This just means if I run this function multiple times, it will continue to minimize or maximize according to the derivative value. Yeah. Now it says, evaluate the function f of x and y with the updated parameters a, b, and c. This simply means, again, compute the forward pass. Yeah? A times x plus b times y plus c. And now it says that the output with the updated values of a, b, and c is negative 3,1707. And it says here, this result should be better than the original result, negative 3.2. Okay, what did we want to do? We wanted to maximize this function, and this is actually larger than this, so we succeeded. Now we have another exercise here which asks from us to write a simple algorithm for binary classification by using the previously written code. Okay, what does this mean to write a simple algorithm? What is the problem with what we did so far? Well, let me show you. What we actually did, we had 6 data points. We took first one, we compared the output of the neural network and the label, decided whether we need to maximize or minimize, and then we updated A, B, C parameters. Yeah, these are the only parameters we need to update. Well, if we continue to do that, then our neural network will actually learn how to correctly classify this one data point. But we do not want that. We want to classify correctly all the data points that we have. And you can ask, how can we do that? Whatever we did for the first data point, we can do for the others. Yeah. So you can, for example, go update the first one, then update the second one, third one, fourth one, fifth one, and sixth one. Yeah. But you do not usually do it one by one. What you do is you randomly initialize one of these points. So you randomly choose, for example, this one, then you update the A, B, and C, then you choose this one, update A, B, and C, choose this one, update A, B, and C, and then finally, if you do it long enough, A, B, and C should be initialized such that when you multiply it with all the data points, the output of the neural network should match the label. Yeah. So in this case, if the label is +1, the output should be greater than 1. And if the label is -1, the output of this multiplication and addition should be less than -1. Okay, so we need to learn a couple of things here. We need to learn how to randomly choose one of these data points, and let's do that. So the first problem is that I would then need to initialize x and y to a new value every time that we run the program, and this is not very useful. It would be better if I could take all the data and all the labels and put it in 2 variables in which all of them would be stored. Yeah. So how can I do that? Actually, here I already implemented the algorithm with the visualizations that could help us to classify the points, which has a lot of code because most of it is about visualizations, and there's a lot of comments explaining what the thing is doing. But I will now just reuse first of these 2 lines of code, and then I'll explain you what they do. So let's copy this one, and in the same line I will copy this one. So these 2 variables, data and labels, now store so-called arrays. Yeah? Array simply means a bundle of things. So now we have, as you can see, this is the first data point, this is the second data point. It's a kind of list. Yeah? First the x value, then comma the y value, x value, comma y value, and then there are 6 of these lists. So it's a list of lists. And finally, the labels are kind of similar, but there is only 6 elements in the list. So how do we access these data points? Okay. You already know about Python indexing. So if I type data, I will just get all of these points. Yeah. But if I say square bracket 0, then I get just the first point. Yeah. If I say data 5, I get, since we start counting from 0, then this will give me the 6th point or the last point. Yeah. In the same way, I can say labels of 5, and this should give me the last label, which is +1. I just need to make sure that indices match for both of these lists. Yeah. So instead of typing here 5, I can try, for example, 6, and then I will get an error because it says this index 6 is out of bounds. It simply means the element with the index 6 doesn't exist. It will be a 7th element, and we have only 6 elements. Okay. Then what I can do is I can make a variable index, and this should be a number between 0 and 5, for example, 4. And now instead of typing here directly 6 and 5, I can just type index. Yeah? And I can type index here. So now I'm taking the 4th index from both of these expressions. If I change the index to 0, I do not need to change this code. It will just give me the data of the first data point and the labels of the first data point. Yeah? Okay, now I need to choose somehow randomly one of these data points. How do I do that? Well, what I could do is I can make this index, which gives me practically a value from 0 to 5. I can make this a random number from 0 to 5, and then if the random number is 5, this will give me the 6th element. If the random number is 0, this will give me the first element. So how do I create these random numbers? There is this NumPy function called mp.random.randint, which will simply give me a natural number between 0 and the number that I specify. So if I say randint of 5, this will give me a random number between 0 and 4. It will never give me 5, yeah? 0, 1, 2, 3, or 4. Just to show you that it will never actually give me 5, what I can do is I could make a so-called loop. What does this mean? So let me show you quickly what does this mean. If I write for I in range of 10, print I, this will print the value of I. And how does this work? So this creates a range of numbers up to 10, and then in each iteration, so when you see this indented block here, in each iteration E gets increased by 1. So E starts as 0, and then it's printed as 0, which you can see here. Then in the next iteration, I becomes 1, and then it's printed as 1, and then this happens up to 9. Yeah. So now I practically can use this expression to do something 1 time or 100 times. Yeah. Okay. And now to show you that this value will never be equal to 5, I can just copy this thing here. So now each time, I do not have to use actually the variable I. This will still assign it and do the loop 10 times. So now I will practically create 10 random numbers, but I do not see them because I'm not printing them. So I can say print each time you create them. And now you can see I get some random numbers, and they are either 0, 1, 2, 3, or 4. Yeah. So there are no 5s. Even if I do it 100 times, you cannot see a 5 there. Yeah. Okay. This is just for me to introduce the concept of looping. And now, as you can imagine, if I run this function with the argument 6, this will be a number between 0 and 5, and then with this number I can randomly kind of index both a data point and its corresponding label. I can just assign this to our index and this will work. But then what is not good here is that I'm kind of hard coding this number 6. Why is it not good? Because what if our data had 15 data points? Then I would need to update this number to 15. Is there a better way to do it? Yes. I can type data.shape. This will give me the shape of the data. So shape 6,2 means there are 6 lists here, and each of these lists have 2 elements. So each list has x and y value. Yeah. So if I'm interested in how many lists there are, I can take this 6. If I want to take this 6, I need to say the data shape of index 0, and then you get the number 6. If I say data shape of index 1, I get the 2. If I just say data shape, I get 6 and 2. Yeah. So with this data shape and taking the index 0, I'm practically asking data to give me its length. So I can now use this, copy it here, and now this will give me a number between 0 and the length of our data. Yeah. So it will never exceed the length of our data. Yeah. And the next thing I can do is I can say that this is now assigned to the variable index. So index is this number between 0 and 6. Yeah? And we can print it. Yeah, print index. So as you can see, it's always a different number, randomly chosen. And now if I say what is the data of this index, yeah, this will give me the corresponding random data point. For example, now the index is 5 and the corresponding data point is this, 2.1 and negative 3.0. Okay, let's call this current data. Current data is now this data point, yeah? And the current label will be this label of the same index, yeah? And now we can print. If I say F, I can then do this. Current data, and I put in this kind of brackets, current data, comma, current label, and I get, for this data point, we have current data is this and current label is this. You see, every time I run it, I get a different index. I can also say here, index, comma, index. And now I can remove this print here. As you can see, index 4, current data, current label. Yeah. Okay, I will remove this not to confuse you. Then, what else can I do? Since I have our current data as two numbers, I can separate them. Yeah, because current data is a list of two numbers. I can say x comma y, because there are two variables, equals current data. Now x will become this one and y will become this one. Yeah. All right. What else do I need to do? Well, I need to initialize a, b, and c, our parameters. Well, we can just copy that from before. I can take these values, a, b, and c. Or I can change them a little bit. Let's make them like this. Yeah, they can be randomly initialized. We do not have to choose them because they will be updated anyway, however you choose them. All right. Then now we have a, b, and c, and we have x and y. Now what we can do is we can compute the output for this current data point, which is selected randomly. So let's do that. We can say output equals a times x plus b times y plus c. And now I can also print f output equals output. I forgot this. Okay, now it runs. So for this index and for this current data point and its label, the output is this. If I run it, I get different outputs. Yeah. Now we have the output and we have the current label. So now we need to compute. We need to say that sign equals to 0. Yeah. Now we need to define the sign according to the relation of the current label and the output. So let's just copy paste that. So this is here. Let's just copy paste it. And make sure that everything is still fine. Well, here it says if the output is greater than -1 and the label is -1. Well, this would work and give you practically an error, yeah? Well, output, let's call it current output. And now copy the current output here, yeah? So we are interested, because the current output is this value here, the variable output we computed beforehand, so I don't want to mix them. So current output is this. And now we are asking if the current output is greater than -1 and label equals to -1. Well, label, we already worked with label somewhere before in our code. Now we are working with the current label, yeah? This is what we actually called. So we need to copy this current label. That would be a mistake if we didn't do this. We always need to make sure when you copy and paste that all the current variables are used. Okay, sign is reinitialized here to 0, so then it's set to -1 or set to +1. Okay, now we know the sign. Then what we need to do is compute our derivative. Okay, let's find that. So here is where we compute the derivative value. So dA, dB, and dC are equal to x, y, and 1. Let's copy this line. Okay, now we computed dA, dB, and dC for x and y, which are currently computed. Okay, the next step is to actually update A, B, and C that we set up here. So let's do that. This is the line. Oh, actually, there is one more thing, which is the step size. Let me just add that on the beginning, because this is something that we do not want to change that often. I will put it behind this A, B, and C. And then let's take this code where we update A, B, and C. Okay, this should be it. To make sure that it works, let's do this. Let's print beforehand what are the values of A, B, and C. So A is equal to A, B is equal to B, and C is equal to C. Okay? And now let's copy this line at the end. So when we update A, B, and C, we want to see if A, B, and C are actually updated. Okay. Let's actually reset A, B, and C to their original values and now run the code. Now it says this is original A, B, and C, and as you can see, they are updated a little bit, yeah? Because the index is 0, current data is this, and current label is 1, but the output is -1. Label says 1, but the output is -1. This means that this function needs to be maximized. And now the function is maximized by actually updating A, B, and C. So what we did now is we did one step of our algorithm for one random point, yeah? Now if we do this more, A, B, and C gets further updated, as you can see, yeah? But I do not want to run this code 100 times in order to make 100 iterations. I can still make this loop that I used to make before, and then computer will run all of this code 100 times. How do I do that? I say for I in range 100, and then I select all of this code and I indent it, and if I run this, you can see that this code is now run 100 times in a row, and A, B, and C are updated. But now the problem is there are a lot of printing here, yeah? So I want to suppress that. I don't want to run this 10,000 times and then have 10,000 prints. They will take the whole screen. Let's then remove these prints, yeah? Okay, I removed the prints by adding this sign before them, hash sign before them, because this makes it into a comment, so this code is then not realized. So now I did it 100 more times, now I did it 100 more times, 100 more times, or 1,000 more times. As you can see, if you never computed before, it's very fast to run such code, yeah? And now finally, I can ask what are A, B, and C. And as you can see, they are quite different than they used to be. They used to be 1, -2, and -1. Now they're 2.37, 1.05, and 0.23. Yeah? So this is what our network has learned, these three values. Now, what does this mean? This means that if we take a data point with certain x and y and label, and if we multiply A by x, add this with B multiplied by y, and add C, the output should match the label. So if the label is +1, the output should be greater than 1. If the label is -1, the output should be less than -1. So let's see if this works. Yeah? How do we do that? So we can, for example, loop through all the input points. We can say for I in range of data shape 0, this will give us, if we print this, this will give us all of these points. So now we can say the index is I, and the current data and current label, and x and y, we can reuse these. Yeah. So current data is data of index. I do not want to use variable index. I want to use variable I, which is the same with this one. I want to use the variable y here for the current label, and now I have x and y and current data. All right. What do I want to do now? I now want to compute the output. Yeah. So now this output will multiply this x and y with these A, B, and C's before, yeah? And I want to print. What? Print. I'm gonna say data point, and then I will put the index I. This gives me data point 0, 1, 2, 3, 4, 5. If I say I plus 1, then this will fix the indices. It will give me data point from 1 to 6. I then want to say label equals to current label. So it gives me the labels for all these data points. And I will ask what is the output. Yeah. So output is current output. And now it tells me what is the output. Yeah. As you can see, the label is 1, but the output is 0.96. The label is -1, but the output is -0.01. As you can see, now I can, by comparing the label and output, I can deduce whether this is correct or not. So how do I do that? I can maybe create a variable called correct, and I will make it false. This is now a Boolean variable, so it can take true or false. It's a kind of logical variable. So I can make it true or false. I will make it false. Yeah, I will assume that our classification is false. And I will ask if the current output is greater than 1 and the current label is equal to 1, then if this happens, then actually this will be a correct prediction. So correct, I will set it to true. But on the other hand, if the current output is less than -1 and the current label is equal to -1, this will also be a true statement. So correct equals to true. Yeah. In all the other cases, correct will still remain false. Okay, this runs. So now I can say here correct. So if the prediction is correct, and then I can put this variable correct here. Okay, for the first data point, the prediction is correct. I can type this prediction. Prediction correct false, prediction correct true, prediction correct true, true, false, true. So you can see we have 1, 2, 3 correct predictions and 3 false predictions. Okay, how can we improve this? So the one way to improve this would be to simply run this algorithm more times. So let's try to do that. I can reinitialize my data, reinitialize my A, B, and C, and then let's run this for 10,000 iterations. If I now type A, B, and C, they're a little bit different. And now, as you can see, that our prediction is actually correct for all the data points, because the label is +1 and the output is greater than +1. When the label is -1, the output is less than -1. And in this way, we have correctly predicted all of the points. Yeah. Now we can say that our model has learned to recognize between points with a label +1 and -1. So to practically recognize between blue and red points. And now let's test if this actually works. And now we can show how prediction actually works. So let's take a point somewhere here. So x should be, for example, -1 and y should be -2. So for this point, as you can imagine that this is the line that separates these two things, this should give me a label -1. This should be a blue point, yeah? So let's make this. So I'll make a variable called x new is going to be -1 and y new is going to be -2. Yeah. And now I will compute a times x new plus b times y new plus c. This gives me -4.305, which means that the label associated with this value should be -1, which means that this point should be blue. Okay, let's do one more example. If I now pick a point, for example, 2, 2, this should be on this side of separation, of the separation between 2 points. And if I pick a point 2 and 2, then the neural network should give me a positive number as an output. Okay, let's do that. X new and y new is 2 and 2. And now if I run it, I get a positive number. So our network is actually correct and predicting. And now I did the same thing here with a simple linear classification algorithm, and I introduced all the steps here. Let's just run this code. So what is different is now I have a more sophisticated way of showing the correct results. Yeah. So I can now plot all of my values. As you can see, the separation of points is a little bit different. Yeah. There are a couple of more functions here which are just used for visualization, and here's the main algorithm. Yeah. Now I made a function, train neural network, where you input data, labels, step size, number of iterations, and the number of iterations where you want to show the results. And if you run this function should try to classify the points and at the same time show you or visualize the classification. So if we run it, you will see that a line is trying to separate these two classes of points. And if you can see, if I run this now, not all of the points are correctly classified. For example, the point 0 is not correctly classified. Well, what can we do to improve this? Well, we can run multiple iterations. We can now, for example, run 2000 iterations. Let's see if it works now. As you can see, with 2000 iterations, we get a completely correct classification of all the points. Yeah? And this is how machine learning works in principle. So this is the most simple case, but then later we will introduce more sophisticated cases with multiple neurons. So that's it. Yeah. Next week we will go to artificial neural networks, which is actually a network of artificial neurons, and we will see how then this improves our learning ability, what changes, how can we actually, the most important thing is how to construct the logistics of these networks, because now input of one network gets into another one, and then you see the input of for example, first network goes into both neurons in the second layer, you see? So how do we then implement this? So this is what we're going to learn next time. But I think for today this was enough. So thanks a lot.